Abstract. Organizations traditionally optimized through linear hierarchies face a fundamental challenge as artificial intelligence transforms business operations: the inability to perceive and manage complex networks. This brief examines graph thinking, the capacity to understand organizational and ecosystem structures as interconnected networks rather than linear processes, as an emergent leadership competency essential for AI integration and strategic resilience. Drawing on network science, organizational theory, and digital transformation research, the analysis demonstrates how graph-literate leaders diagnose hidden dependencies, protect critical relationship nodes, and architect contexts that enable human-AI collaboration. Evidence from platform companies reveals graph thinking as foundational to AI leadership advantage, while cases across healthcare, manufacturing, and services illustrate consequences of network blindness. The brief synthesizes evidence-based interventions, network mapping protocols, betweenness analysis, edge quality assessment, and ecosystem density optimization, alongside frameworks for building long-term network intelligence capabilities. As AI agents require explicit relationship architectures that human workers navigate implicitly, graph thinking transitions from technical specialty to core strategic competence, determining which organizations successfully integrate intelligent systems into collaborative workflows. For over a century, management theory optimized organizational performance through hierarchical structures, linear workflows, and sequential processes. Taylor, 1911. Fayol, 1949. The geometry of effective management appeared Euclidean. Shortest paths between objectives followed straight lines. Value chains flowed unidirectionally, and organizational charts mapped authority through vertical layers. This linear paradigm served industrial-era enterprises well. When complexity remained manageable through decomposition and coordination occurred primarily within defined boundaries. Chandler, 1962. Today, that paradigm faces fundamental challenges. Organizations operate as complex adaptive systems embedded within broader ecosystems, where outcomes emerge from intricate webs of relationships rather than linear cause-effect chains. Anderson, 1999. Stacy, 2001. Digital transformation has accelerated this shift. Platform businesses dominate global markets not through superior products alone, but through architectural advantages rooted in network effects and relationship economics. Parker et al. 2016. Meanwhile, artificial intelligence transitions from passive tools to active agents, requiring organizational architectures that make implicit knowledge and relationships machine-readable. Fountain et al. 2019. The practical stakes are considerable. Leaders make apparently isolated decisions: budget cuts, policy changes, structural reorganizations, only to encounter unexpected consequences months later in seemingly unrelated domains. Revenue stalls following field service reductions. Patient safety deteriorates after metric optimization. Innovation slows following supplier consolidation. These failures don't reflect poor judgment or inadequate analysis. They represent perception gaps. Leaders attempt to manage networks using conceptual frameworks designed for hierarchies. This brief examines graph thinking as an emergent leadership competency, the capacity to perceive, analyze, and architect organizational and ecosystem structures as interconnected networks. Drawing on network science, organizational behavior research, and digital transformation evidence, we demonstrate how graph-literate leaders diagnose systemic vulnerabilities, protect critical relationship infrastructure, and design contexts enabling effective human-AI collaboration. The analysis proceeds through three movements. First, establishing graph thinking's conceptual foundations and empirical significance. Second, documenting organizational consequences of network blindness versus network intelligence. Third, synthesizing evidence-based interventions and long-term capability-building frameworks. The network intelligence landscape defining graph thinking in strategic leadership. Graph thinking represents a fundamental shift in how leaders conceptualize organizational structure and dynamics. Rather than viewing enterprises as hierarchical pyramids or linear value chains, graph thinking perceives organizations as networks, collections of nodes, people, teams, partners, systems, connected by edges, relationships, information flows, dependencies, influences, that collectively determine performance. Borgatti and Foster. 2003. This perspective draws directly from network science, an interdisciplinary field examining how relationship structures shape system behavior across domains from biology to sociology. Barabasi. 2016. Applied to organizations, network science provides diagnostic frameworks for understanding phenomena invisible to traditional analysis. Why some individuals wield disproportionate influence regardless of formal authority. Why certain teams innovate prolifically while others stagnate despite equivalent resources. Why specific partnerships create outsized value while others drain energy. Cross and Parker. 2004. Reagans and McEverly. 2003. Graph thinking encompasses several interconnected capabilities. First, structural perception, the ability to see beyond org charts to actual relationship architectures determining information flow. Decision velocity and collaborative capacity, Krackhard and Hansen. 1993. Second, dependency mapping, tracing how decisions and events propagate through networks. Identifying critical paths and potential failure cascades, Lorenz et al. 2009. Third, position analysis, recognizing that value creation often derives from network location rather than individual output alone, with certain positions controlling information bottlenecks or bridging otherwise disconnected clusters. Burt. 2004. Fourth, ecosystem architecture, understanding that organizational boundaries are permeable, with performance determined by relationship quality across suppliers, partners, customers, and even competitors. Janciti and Levian. 2004. Importantly, graph thinking isn't purely analytical, it's diagnostic and interventional. Graph-literate leaders don't merely map networks. They actively shape them, strengthening critical edges, reducing harmful path lengths, building redundancy where resilience matters, and architecting relationship structures that align human intuition with machine intelligence. Borkundi and Kilduff. 2006. State of practice, platform leaders and the graph thinking advantage. The strategic significance of graph thinking becomes evident when examining digital platform leaders, companies that have fundamentally restructured global markets over the past 2 decades. Amazon, Netflix, Meta, formerly Facebook, and Google share a common foundation. Each built competitive advantage through explicit graph architectures that traditional enterprises treated as implicit or ignored entirely. Hagu and Wright. 2015. Amazon's purchase graph maps billions of relationships, which products customers view together. Purchase sequences, browsing patterns before conversion, and how these networks evolve across segments and time. Linden et al. 2003. This graph architecture enables recommendation systems that have become central to Amazon's revenue generation, and provides the foundational data infrastructure for Amazon's AI capabilities. From demand forecasting to inventory optimization to AWS machine learning services. Smith and Linden. 2017. Netflix developed a content graph linking viewing preferences, engagement patterns, content attributes, and viewer characteristics across hundreds of millions of subscribers. Gomez Uribe and Hunt. 2016. This graph thinking enabled not just personalization algorithms that significantly improved customer retention, but strategic content investment decisions, production optimization, and AI-driven systems that now shape everything from thumbnail selection to optimal episode release timing. Meta built a social graph representing relationship structures among billions of people, connections, interactions, influence patterns, and community formations. Wilson et al. 2009. This graph architecture creates network effects that constitute Meta's primary competitive moat while providing the training data and architectural foundation for Meta's AI systems. From content recommendation to language models to planned future AI agents operating within social contexts. Google's knowledge graph and search graph map relationships among concepts, entities, queries, and web content. Brin and Page, 1998. These graph architectures transformed search from keyword matching to semantic understanding, enabling Google's AI evolution from search algorithms to generative AI systems that leverage decades of relationship mapping. A pattern emerges: companies that structured themselves around graphs now lead AI adoption and deployment. Brynjolfsson and McAfee. 2017. This isn't coincidental. Graph thinking provided these organizations with three critical advantages as AI matured. First, data architecture. Years of explicitly mapping relationships created training datasets and operational infrastructures AI systems could leverage. Second, leadership mindset. Executives accustomed to thinking in networks more readily understood AI integration challenges than leaders thinking linearly. Davenport and Ronanke. 2018. Third, organizational structure. Companies built around relationship economics developed collaborative workflows and boundary-spanning capabilities that traditional hierarchies lacked. Pernom et al. 2014. Traditional enterprises face a graph thinking deficit. Research examining AI adoption across industries reveals that technical capabilities and financial resources explain less variance in successful AI integration than organizational readiness factors. Particularly leadership capacity to perceive and architect complex relationship structures. Ransbotham et al. 2019. Companies attempt to bolt AI onto linear structures, expecting agents to navigate organizational complexity that remains unmapped and implicit, a fundamental architectural mismatch. Organizational and individual consequences of network blindness. Organizational performance impacts. Organizations that fail to adopt graph thinking face systematic performance degradation, often in ways leadership cannot diagnose because the causal mechanisms remain invisible to linear analysis. Research across sectors documents these consequences through multiple channels. Strategic implementation failure represents perhaps the most significant organizational impact. Studies of strategic initiative success rates reveal that 50 to 70% of major organizational change efforts fail to achieve intended outcomes. Beer and Nohria. 2000. Cotter, 1995. While traditional explanations emphasize resistance to change or inadequate communication, network analysis reveals structural factors. Initiatives fail because leaders cannot trace dependency paths through organizational networks, underestimate blast radius of decisions, or inadvertently disrupt critical relationship bridges. Tushman and O'Reilly. 1996. A healthcare study examining hospital performance variation found that clinical outcome differences across institutions with equivalent resources and protocols correlated strongly with network density within care teams, specifically the number of actual communication pathways relative to possible pathways. Creswick and Westbrook. 2010. High-density networks enabled rapid information sharing, collaborative problem-solving, and collective learning. Low-density networks fragmented care, created information silos, and prevented pattern recognition across cases. Linear analysis focusing on individual clinician competence or equipment availability missed the relationship architecture determining performance. Manufacturing research demonstrates supply chain vulnerability deriving from network structure rather than individual supplier reliability. When automotive manufacturers consolidated supplier bases to gain negotiating leverage, They reduced network density and increased betweenness centrality of remaining suppliers, Choi and Hong. 2002. The 2011 Japan earthquake and subsequent disruptions revealed consequences. Companies with denser supplier networks, more redundant pathways, recovered significantly faster than those with sparse networks optimized for efficiency, Sheffy and Rice. 2005. Graph-blind cost optimization created fragility invisible until disruption. Innovation performance shows similar network dependencies. Research examining R&D productivity across technology firms found that invention rates correlated more strongly with network structural holes, positions spanning otherwise disconnected clusters, than with individual researcher credentials or R&D spending levels, Burt. 2004. Fleming et al. 2007. Organizations that inadvertently eliminated high betweenness positions during restructuring experienced innovation collapse 12 to 18 months later. A lag that prevented leaders from connecting cause and effect, Reagans and Zuckerman. 2001. AI integration challenges increasingly reflect graph thinking deficits. Analysis of AI pilot projects across industries reveals that technical performance typically meets or exceeds expectations. Yet most pilots fail to scale beyond initial use cases, Fountain et al. 2019. Ransbotham et al. 2019. The bottleneck isn't technology, it's organizational architecture. AI agents require explicit relationship mapping. Which systems connect to which processes? What dependencies exist between teams? How information flows across boundaries? Organizations lacking explicit graph architecture cannot provide context AI systems need. Limiting deployment to narrow, well-defined sandboxes. Platform companies excel at AI precisely because they built graph infrastructure years before AI agents arrived. Individual and stakeholder well-being impacts. Network blindness creates human costs extending beyond organizational performance metrics, affecting employee well-being, customer experience, and broader stakeholder outcomes. Talent retention correlates significantly with network position. Research examining employee turnover finds that departure likelihood depends less on compensation or job satisfaction than on social integration, specifically the number and quality of meaningful work relationships, Mossholder et al. 2005. Employees with high clustering coefficients, strongly connected to colleagues, and low betweenness centrality, not isolated bridges, show significantly lower turnover probability, Crackhard and Porter. 1986. Organizations that restructure without considering network effects inadvertently isolate previously integrated employees, triggering departures that appear inexplicable from linear HR analysis. The bridge node phenomenon creates particular well-being challenges. Employees with high betweenness centrality, those connecting otherwise disconnected organizational clusters, face disproportionate cognitive load, role ambiguity and burnout risk. Obstfeld, 2005. Sparrow et al. 2001. These individuals translate across functional languages, broker information between silos, and maintain relationships spanning boundaries. They're invisible heroes, often unrecognized because their value derives from position rather than output. Network blind management treats them as average performers, failing to protect or support them appropriately until they depart and organizational path lengths suddenly expand, Cross et al. 2010. Customer experience increasingly depends on organizational network quality. Research in service industries demonstrates that customer satisfaction correlates with network density among frontline employees, specifically how well service workers can access expertise and resources across organizational boundaries, Jasmine et al. 2012. Low-density networks force employees to provide suboptimal service because they cannot rapidly connect customers to solutions residing elsewhere in the organization. Graph-thinking organizations architect high-quality edges between customer-facing roles and back-end expertise, reducing path length from customer need to organizational capability. Healthcare provides stark evidence of patient well-being impacts. Studies of adverse event rates reveal that clinical errors correlate with care team network fragmentation, multiple handoffs, poor information continuity, and weak edges between specialties. Sutcliffe et al. 2004. Network analysis of hospitals experiencing patient safety incidents consistently identify structural factors, critical information trapped in disconnected clusters, decision-makers lacking visibility to relevant expertise, and coordination failures at organizational boundaries. Benham Hutchins and F. Ken. 2010. Linear root cause analysis blames individual errors. Graph analysis reveals systemic network deficiencies. Evidence-based organizational responses network mapping and diagnostic protocols. Organizations beginning graph-thinking journeys require systematic approaches to making implicit networks explicit. Research across sectors has identified effective mapping and diagnostic protocols that translate network science concepts into actionable leadership practices. Organizational network analysis, ONA, provides the foundational methodology. ONA systematically maps relationships within and across organizational boundaries, typically through surveys asking employees about communication patterns, advice-seeking relationships, and collaborative ties. Cross and Parker. 2004. Advanced implementations incorporate digital trace data, email networks, collaboration platform activity, project team compositions, to supplement survey data with behavioral evidence. Kleinbaum et al. 2013. Effective ONA implementations follow several principles validated through research. Start with strategic questions, not comprehensive mapping. Organizations attempting to map entire relationship networks often drown in data without actionable insights. Successful implementations begin with focused questions. Where are critical information bottlenecks? Which teams are unexpectedly disconnected? Who bridges important organizational divides? Cross et al. 2002. Combine structural metrics with qualitative interpretation. Network metrics like betweenness, centrality, or clustering coefficients reveal what patterns exist. But understanding why those patterns matter and how to intervene requires coupling quantitative analysis with interviews and observations. Borgatti et al. 2018. Map both formal and informal networks. Org charts show intended structure. Actual networks show functional reality. High-performing organizations often show significant divergence, with informal networks compensating for formal structure deficiencies. Krackhard and Hansen. 1993. Include ecosystem boundaries in mapping scope. Organizations aren't closed systems. Critical relationships extend to suppliers, partners, customers, and adjacent industries. Comprehensive network mapping incorporates these external nodes and edges. Provan et al. 2007. Microsoft deployed ONA when examining collaboration patterns across product divisions, discovering that certain mid-level engineers served as critical bridges between groups that otherwise never communicated. Cross and Thomas. 2008. These individuals weren't in leadership positions and received average performance ratings. Yet network analysis revealed they enabled information flow worth millions in avoided redundancy and accelerated problem solving. Microsoft restructured roles to protect these network positions and created systematic programs to identify and support employees in bridge positions across the organization. Kaiser Permanente implemented network mapping to understand care coordination patterns, revealing that registered nurses frequently occupied positions with extremely high betweenness centrality. They connected physicians, specialists, pharmacists, and patients but received neither recognition nor support commensurate with their network importance. Creswick and Westbrook. 2010. Analysis showed that nurse turnover in high betweenness positions triggered care fragmentation cascades affecting dozens of patients. Kaiser redesigned care team structures to reduce nurse betweenness, distributing coordination more evenly, while simultaneously increasing compensation and career development for nurses in unavoidably high betweenness roles. Procter & Gamble used network mapping when integrating acquired companies, specifically identifying employees whose departure would fracture critical knowledge networks. Hansen, 2009. Rather than applying uniform retention incentives, P&G targeted individuals with high betweenness centrality for specialized retention packages and deliberately built redundant pathways around them during integration periods, reducing network fragility. Edge quality assessment and optimization beyond mapping network structure. Graph-thinking organizations systematically assess and improve relationship quality, the edges connecting organizational nodes. Research demonstrates that edge quality often matters more than network topology alone. Reagans and McEverly, 2003. Strong versus weak ties represent a fundamental edge quality dimension. Strong ties, characterized by frequent interaction, mutual trust, and reciprocal exchange, enable rich information transfer and tacit knowledge sharing but require significant maintenance investment. Granovetter, 1973. Weak ties, more distant relationships with infrequent contact, provide access to novel information and diverse perspectives but cannot transfer complex or context-dependent knowledge. Hansen, 1999. Strategic edge quality optimization involves diagnosing tie strength requirements by function. Innovative teams benefit from weak ties bringing diverse inputs. Execution teams need strong ties enabling tight coordination. Organizations often default to uniform relationship architectures when different functions require different edge qualities. Obstfeld, 2005, identifying adversarial edges requiring redesign. Some organizational edges carry negative information flow, blame attribution, turf protection, metric gaming. Network analysis can identify adversarial edges that traditional assessment misses. Cassiaro and Lobo, 2008, creating shared metrics and joint accountability at critical edges. When organizational units optimize locally using disconnected metrics, edges between them become adversarial. Joint metrics realign incentives, transforming adversarial edges into collaborative ones. Simons, 1995, building redundancy at high-risk edges. Some edges are so critical that their failure catastrophically degrades network function. Graph-thinking leaders identify these edges and deliberately build parallel pathways as backup. Lorenz et al. 2009, Toyota's production system exemplifies systematic edge quality management. Toyota deliberately created strong ties within work teams, enabling tacit knowledge transfer for continuous improvement, while maintaining weak ties across teams, enabling problem-solving expertise to flow when needed. Dyer and Nobioka, 2000. The Anden chord system and production floor layout physically manifest this edge architecture. Strong local ties for normal operation, weak cross-cutting ties for exception handling. Cisco addressed collaboration quality between product engineering and customer success teams by creating shared customer health metrics owned jointly by both functions. Galotti, 2007. Previously, engineering optimized feature delivery while customer success managed retention, disconnected metrics creating adversarial edges. Joint ownership transformed the edge from adversarial to collaborative, with engineering proactively seeking customer success input during development and customer success providing early feedback, reducing post-release issues. Zara's fast fashion business model demonstrates extreme edge optimization across ecosystem boundaries. Ferdows et al. 2004. While competitors focused on efficiency through long-term supplier contracts, sparse networks with high individual edge efficiency Zara built a dense network of geographically proximate suppliers with whom they maintained frequent communication and rapid iteration cycles. Higher individual edge costs were offset by network-level agility. Zara could respond to fashion trends in weeks while competitors required months. Graph thinking revealed that ecosystem density mattered more than individual edge efficiency. Betweenness analysis and bridge protection organizations frequently undervalue or inadvertently destroy critical network positions, individuals, teams, or partnerships serving as bridges connecting otherwise disconnected parts of the system. Research demonstrates that protecting and developing bridge positions yields disproportionate returns. Burt, 2004. Obstfeld, 2005. Betweenness centrality measures how often a node sits on the shortest path between other nodes in the network. High betweenness indicates bridge positions. Remove the node and path lengths increase dramatically or become infinite. Borgatti and Everett, 2006. From a strategic perspective, high betweenness nodes control information flow, enable cross-silo collaboration, and often drive innovation by recombining knowledge from disconnected domains. Fleming et al. 2007. Effective betweenness management involves systematic identification of bridge positions. Network analysis reveals individuals occupying critical bridges, often mid-level employees whose titles don't reflect network importance. Qualitative validation confirms whether high betweenness reflects genuine value or merely structural position without actual information transfer. Cross et al. 2010. Retention and development of bridge individuals. High betweenness individuals face burnout risk from serving multiple constituencies while receiving average compensation based on hierarchical position. Graph thinking organizations provide specialized retention incentives. Career paths and workload management. Obstfeld, 2005. Building redundancy around critical bridges. When betweenness concentrates in single individuals, organizations face catastrophic risk from departure, illness, or capacity constraints. Creating backup bridges, either developing additional people in similar positions or strengthening alternative pathways, reduces fragility. Reagans and Zuckerman, 2001. Distinguishing valuable versus problematic betweenness. Some high betweenness positions reflect bottlenecks rather than value creation. Single approval authorities or information gatekeepers who slow rather than enable work. Graph thinking leaders distinguish between bridges that should be protected versus those that should be eliminated through structural redesign. Cross et al. 2002. IBM identified through network analysis that certain technical architects occupied critical bridge positions between product development, sales engineering, and client services, three groups that otherwise rarely communicated. Lesser and Stork, 2001. These architects weren't in senior positions, but their betweenness enabled IBM to translate client needs into technical solutions while keeping development informed of market requirements. IBM created a formal, distinguished engineer career track specifically to retain and develop high betweenness technical roles without requiring they move into management. Cleveland Clinic discovered that certain physician liaisons, physicians who split time between clinical practice and administrative coordination, had extremely high betweenness, connecting clinical departments to operational management. These positions faced high burnout and turnover despite their criticality. Cleveland Clinic restructured by reducing clinical loads for liaison physicians, acknowledging that coordination value exceeded incremental clinical value. Increasing compensation, and deliberately developing backup liaisons to reduce single point of failure risk. IDEO, the design consultancy, explicitly manages betweenness through project staffing. Hargadon and Sutton, 1997. When forming project teams, IDEO deliberately includes individuals with ties to different knowledge domains and previous project experiences. This creates high project-level betweenness, enabling teams to access diverse organizational knowledge. IDEO treats betweenness as a staffing criterion, Teams need members who bridge to relevant expertise networks, not just members with direct domain knowledge. Path length reduction and information velocity. Organizations often suffer from excessive path length, the number of steps required for information, decisions, or resources to travel from one part of the system to another. Long path lengths create delays, information degradation, and coordination failures. Cross and Parker, 2004. Graph thinking leaders systematically identify and reduce problematic path lengths. Research demonstrates several path length reduction strategies, creating direct edges between previously disconnected nodes. When analysis reveals long paths between functions that should coordinate closely, the simplest intervention is establishing direct relationships, joint meetings, co-located staff, shared communication channels. Allen, 1977, introducing hub nodes that reduce average path length. In some contexts, creating central coordination roles or teams reduces network-wide path length more efficiently than creating all pairwise connections. Barabasi and Albert, 1999, eliminating unnecessary intermediary steps. Some path length stems from bureaucratic processes that don't add value. Network analysis can reveal where streamlining eliminates steps without losing important control or coordination. Cross et al. 2002, empowering edge nodes to act without routing through centers. Hierarchical structures often force information to flow up to central nodes before being redistributed, creating long paths and bottlenecks. Distributed decision-making authority reduces path length by enabling direct edge-to-edge communication. Pernom et al. 2014, Amazon reduced path length from customer feedback to product improvement through its two-pizza team structure. Rather than customer insights flowing through multiple layers, customer service, regional management, product management development teams. Amazon empowered small autonomous teams to directly access customer data and make product decisions. Path length from customer to fix dropped from 5 to 7 steps to 1 to 2 steps, dramatically accelerating iteration cycles. Spotify addressed path length between cross-functional expertise and product teams by creating a matrix structure of squads, autonomous product teams, and chapters, functional expertise networks. This architecture reduced path length in both directions. Squads could access specialized expertise without routing through management hierarchy, and chapters could distribute knowledge without waiting for formal training cycles. While the model faced implementation challenges in practice, the graph thinking logic, designing for reduced path length while maintaining necessary coordination, proved influential across the technology industry. Morningstar, a large tomato processing company, eliminated hierarchical management entirely, instead using a colleague letter of understanding (CLOU) system where employees directly negotiate commitments with whoever they need to coordinate with. Hamill, 2011. This radical reduction in path length enabled rapid problem solving and eliminated approval bottlenecks. While not appropriate for all contexts, Morningstar demonstrates that dramatically reducing path length can work even in traditional industries when organizational culture and systems support it. Ecosystem density optimization and resilience building. Graph thinking leaders recognize that organizational boundaries are permeable and strategic performance depends on ecosystem density, the richness of relationships extending to suppliers, partners, customers, and adjacent players. Yanciti and Levian, 2004. Research demonstrates that ecosystem network structure often determines competitive outcomes more than firm-level capabilities alone. Adner, 2017. Strategic ecosystem density management involves mapping ecosystem relationships as explicitly as internal networks. Most organizations thoroughly map internal structure while treating ecosystem relationships as contractual rather than network phenomena. Comprehensive mapping reveals where ecosystem is too sparse, creating vulnerability, or relationships are too dependent on single paths. Provan et al. 2007. building redundancy in critical pathways. While efficiency logic favors consolidating to single suppliers or exclusive partnerships, resilience requires redundant pathways. Graph thinking leaders consciously trade some efficiency for network resilience, particularly for mission-critical dependencies, Sheffy and Rice. 2005, Cultivating Weak Ties Across Ecosystem Boundaries. Organizations often maintain strong ties only with current partners while lacking relationships to potential alternatives. Weak ties to non-current partners provide options and market intelligence without the maintenance costs of strong ties. Uzi. 1997, Balancing Network Density Against Coordination Costs. While resilience increases with ecosystem density, coordination costs also rise. Optimal density depends on environmental volatility. Stable environments favor sparse networks, efficiency. Turbulent environments favor dense networks, adaptability. Davis et al. 2009, Apple manages ecosystem density strategically across different components. For differentiated technologies, processors, software, Apple maintains sparse networks with tight control, few partners. Long-term exclusive relationships optimized for coordination efficiency. For commoditized components, memory, standard parts, Apple maintains dense supplier networks enabling rapid switching and price competition. This differentiated density strategy balances control where it matters with resilience where it's needed. Toyota's supplier network demonstrates deliberate density optimization. Beyond first-tier suppliers, Toyota maintains relationships with second- and third-tier suppliers, creating network density that enables rapid problem-solving and innovation. Dyer and Nobioka. 2000. When quality issues arise, Toyota can trace problems deep into the supply network because relationships exist. Competitors maintaining only first-tier relationships face longer problem resolution cycles because they must work through intermediaries. During COVID-19 disruptions, medical device manufacturers with dense supplier networks adapted faster than competitors with sparse networks. Organizations with existing weak ties to alternative suppliers could rapidly shift production when primary sources became unavailable, while competitors lacking those network relationships faced extended delays establishing new partnerships. The crisis revealed that network density provided adaptability insurance worth far more than the maintenance costs during normal operations. Building long-term network intelligence capabilities. Developing leadership network literacy while specific network interventions produce immediate value. Sustainable advantage requires building network literacy as a core leadership competency. Leaders who instinctively see in graphs, diagnose through network lenses, and design interventions considering systemic effects. Research on expertise development suggests several pathways for cultivating network literacy. Formal education in network science fundamentals. Leaders need basic literacy in network concepts, nodes, edges, centrality measures, clustering, path length, and ability to interpret network visualizations. This doesn't require deep technical expertise but sufficient understanding to ask intelligent questions and evaluate network analyses. Borgatti et al. 2018. Practice through organizational network analysis. Conceptual understanding deepens through application. Leaders who participate in mapping their own organizational networks identify surprises between expected and actual structures, and design interventions based on network insights develop richer understanding than those who only study concepts. Cross and Parker. 2004. Exposure to network-native organizations. Learning from companies built around graph thinking, platforms, open source communities, network-centric nonprofits, accelerates literacy development. Observing how network-native leaders talk about structure, make decisions, and solve problems provides templates for application in traditional contexts. Parker et al. 2016. Rotating through high betweenness positions. Leaders who have personally experienced bridge roles, connecting across functions. Translating between technical and business contexts. Spanning organizational boundaries, develop intuitive understanding of betweenness dynamics that pure conceptual training cannot provide. Obstfeld. 2005, General Electric incorporated network thinking into leadership development by requiring executives to conduct O&A projects in their business units and present findings to peers. Cross and Thomas. 2008. This experimental approach created cohorts of leaders fluent in network concepts and comfortable applying network analysis to strategic decisions. When GE later deployed digital initiatives, these network-literate leaders understood integration challenges that traditional hierarchical thinkers missed. U.S. Army Special Operations Command developed network literacy through operational experience. Special operations forces operate through network structures rather than hierarchical command, requiring leaders to think in terms of relationships, path lengths, and distributed coordination. McChrystal et al. 2015. Rotating conventional force officers through special operations assignments exposed them to network-centric operations, building literacy they carried to subsequent conventional assignments. The Army deliberately used organizational rotation as a literacy development mechanism. Leading technology companies build network literacy through their organizational cultures, which explicitly emphasize relationship networks extending to employees, customers, partners, and communities. New leaders are immersed in network-centric thinking from onboarding. Success metrics include relationship building, cross-functional collaboration, and ecosystem engagement rather than purely individual output. This cultural emphasis cultivates network literacy as ambient organizational knowledge rather than specialized expertise. Integrating network analysis into strategic planning, organizations frequently maintain separation between strategic planning processes and network analysis, treating networks as diagnostic tools for specific problems rather than foundational inputs to strategy formulation. Long-term network intelligence requires integrating graph thinking into core strategic processes. Gallotti et al. 2000. Effective integration involves, including network mapping in environmental scanning. Traditional strategic analysis examines industry structure, competitive positioning, and market trends. Network-enhanced analysis also maps ecosystem relationships, identifies critical dependencies, and tracks network evolution over time. Yanciti and Levian. 2004. Evaluating strategic options through network implications. When considering strategic alternatives, acquisitions, partnerships, market entries, organizational restructuring, systematically assess network effects. How does this option change our relationship architecture? Create new dependencies. Eliminate critical bridges. Increase or decrease ecosystem density. Provan et al. 2007. Setting network health metrics alongside financial metrics. Organizations extensively track financial and operational KPIs but rarely monitor network health. Strategic scorecards should include network metrics, average path length to critical capabilities, ecosystem density in key domains, concentration risk in high betweenness relationships, quality indicators for critical edges. Cross et al. 2009. Conducting network scenario planning. Traditional scenario planning explores alternative futures through market and technology lenses. Network scenario planning examines how ecosystem relationships might evolve. What happens if critical partners fail or become competitors? And how network structure would need to adapt under different scenarios. Adner. 2017. Cisco integrated network analysis into acquisition strategy by mapping technology ecosystem relationships before pursuing targets. Gallotti. 2007. Rather than evaluating acquisition candidates solely through product fit or financial metrics, Cisco assessed network position. Did the target bridge critical technology domains? Provide access to customer or developer communities Cisco lacked. Create redundancy in relationships where Cisco faced concentration risk. This network-augmented due diligence helped Cisco achieve high acquisition success rates in an industry where most acquisitions fail. Cleveland Clinic incorporated network health metrics into strategic planning after discovering that patient outcomes correlated strongly with care team network density. Strategic planning now includes specific targets for care coordination network metrics, density within multidisciplinary teams, path length from primary care to specialist consultation, and betweenness distribution to avoid overconcentration. Tracking these metrics alongside traditional quality and financial measures keeps network architecture visible in strategic decisions. Nokia's mobile device decline illustrates the strategic risks of network blindness. While Nokia focused on product innovation and manufacturing efficiency, Apple and Google built ecosystem graphs, app developer networks, content provider relationships, and platform complementers. Nokia eventually recognized its ecosystem deficit. But by then network effects had locked in competitors' advantages. Earlier network-aware strategic planning might have revealed ecosystem architecture as the decisive competitive dimension, prompting different strategic choices while options remained available. Creating network-aware organizational design. Traditional organizational design optimizes hierarchical structures, spans of control, reporting relationships, functional groupings, and centralization versus decentralization. Graph-thinking organizational design additionally considers network properties, how structural choices affect path lengths, where betweenness will concentrate, what edge qualities different structures enable, and how formal design interacts with emergent informal networks. Pernom et al. 2014. Network-aware organizational design principles include deliberately architecting for appropriate path lengths. Some functions require short paths, customer problem to engineering fix. Others tolerate longer paths, routine policy questions. Rather than default hierarchies, design structures that create path lengths matching coordination requirements. Cross and Parker. 2004. Distributing betweenness to avoid bottlenecks and burnout. Traditional hierarchies concentrate betweenness in management layers. Network-aware design distributes coordination across multiple nodes, reducing bottleneck risk and cognitive load on any single position. Cross et al. 2010. Creating boundary-spanning roles and structures. Organizations need individuals and teams explicitly chartered to bridge across functions, geographies, or ecosystem boundaries. Making these bridge roles formal rather than emergent enables appropriate selection, support, and performance management. Tishman and Scanlon. 1981. Designing for both efficiency and resilience through network redundancy. Pure hierarchical efficiency minimizes redundant relationships. Network-aware design deliberately includes backup pathways for critical connections. Trading efficiency for resilience. Lorenz et al. 2009. Aligning formal structure with informal network realities. Rather than assuming informal networks will conform to formal structures, network-aware design acknowledges and works with emergent relationship patterns, where informal networks consistently contradict formal structures. Consider whether formal design should adapt. Crackard and Hansen. 1993. Valve Corporation designed an organizational structure explicitly around network principles rather than hierarchical ones. Employees aren't assigned to managers or permanent teams. Instead, they join project networks based on interest and perceived value. Compensation depends partly on peer assessment of network contribution, whether colleagues sought your expertise, whether you effectively bridged knowledge domains. While Valve's pure network structure isn't appropriate for most organizations, it demonstrates possibility of building formal structures around graph principles. W. L. Gore, maker of Gore-Tex, uses a lattice structure designed to keep path lengths short and distribute betweenness, Hamill. 2007. Rather than hierarchical layers, Gore maintains flat structures where employees, called associates, connect directly with whoever they need to collaborate with. Leaders emerge through network position, those who attract followers based on expertise and relationship quality, rather than appointment. Gore deliberately keeps facilities under 200 people to maintain network density where everyone can potentially know everyone. Haier, the Chinese appliance manufacturer, restructured into thousands of microenterprises connected through market-like mechanisms rather than hierarchical control. While individual microenterprises remain small, maintaining high internal density. The overall structure creates flexible network topology that adapts to changing conditions. Haier consciously traded hierarchical control for network adaptability, demonstrating that network-aware design can scale to very large organizations. Building human-AI collaborative network architecture as AI agents become active participants in organizational work rather than passive tools. Graph thinking becomes essential for architecting effective human-AI collaboration. Research on human-AI teamwork reveals that success depends less on algorithm sophistication than on relationship architecture, how clearly roles are defined, how information flows between human and AI agents, and how work is coordinated across boundaries. Wilson and Doherty. 2018. Human-AI collaborative network architecture requires explicit knowledge graphs encoding organizational context. Human employees navigate organizations using tacit knowledge, who knows what, which teams coordinate naturally, what dependencies exist between systems. AI agents need this knowledge made explicit through knowledge graphs mapping concepts, entities, relationships, and processes designing complementary rather than redundant relationships. Effective human-AI collaboration assigns responsibilities based on comparative advantage, humans for context understanding and ethical judgment, AI for pattern recognition and processing scale. This requires architecting edges that enable each to contribute strengths rather than competing in same domains. Brynjolfsson and Mitchell. 2017. Creating feedback loops that improve both human and AI capabilities. Human-AI relationships should enable mutual learning. Humans provide context that improves AI performance. AI provides insights that develop human understanding. Network architecture must support bidirectional information flow and learning. Reich and Krakowski. 2021. Maintaining human oversight of critical decisions without creating bottlenecks. AI agents can increase decision velocity, but important choices still require human judgment. Network architecture must balance oversight needs with speed, not routing every AI action through human approval, which recreates hierarchical bottlenecks, while ensuring human review of consequential decisions. Fountain et al. 2019. Building resilience through human-AI redundancy on critical paths. Pure automation creates single point of failure risk when AI systems fail. Network-aware architecture maintains human capability to perform critical functions if AI fails, while also enabling AI to support humans when they are overwhelmed. Ensley. 2017.